So we're going to move on to the next section in internal forces. So this again where we've been dealing with systems that we're interested in cutting open and finding out what the internal forces are. And we're going to talk about a very specific approach or a very specific problem that we need to solve for internal forces called shear and moment diagrams. And so the question that we have here is, let's say we have this beam. So here's a beam. It's got a 4 kilonewton per meter distributed load, a 2 kilonewton meter, and then it has a pinned support, of course, and a roller support, and the dimensions that we see below. And the question that we want to ask is, I want to draw a continuous graph, so to speak, or a continuous diagram of the values of the shear and moment as I march through this beam at any point, right? So take a cut here, 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 etc., etc. Just look at the internal moments and shears at every single point along this beam. The reason we do this is because that helps us design the beam later on when we go to mechanics of materials. But for right now, we're just interested in sort of the flow of the force, so to speak, through the beam. All right, so let me get rid of everything there and replace the reactions with their forces that they should have. So AY, BY. We can see just by observing, right, that AX here is going to be equal to 0 because there's no forces in the X. So the only forces we're going to have are upright. All right, we can do some moments about A equals 0, and that will lead us to the value of a value for By, which is given to us by 3.2 kilonewtons, or given, it turns out to be 3.2 kilonewtons. And then we can do some forces in Y equals 0 globally. Again, this is for the whole beam, and get AY equal to 6.8 kilonewtons. All right, so by doing first global equilibrium, we can find our two reaction forces, AY and BY. Now we can go on to the process of thinking about how to create the shear and moment diagram. All right, and so the way that we're going to do this is we're going to realize that we need basically to create a series of piecewise continuous functions as we travel through this beam. And that really boils down to identifying regions where the loading is constant. So in this case, that would be from A to C, right? Because that's where we have that continuous distributed load and no changes. Then from C to D, because this has a point load here, and obviously that's a change in load. And then finally from D to B. So we've got 1, 2, 3 regions in this beam that we're going to go ahead and have to construct a free body diagram for, and then solve for the internal forces at that point. All right. One other thing about shear and moment diagram. So let's go ahead and do this. So we're going to start with A to C. Actually, I'm going to, let's erase this. Ooh. Sorry. It got shoved over there. Let's erase this. I'm going to redraw this thing. AY, and then BY, and then we're just going to keep the points. AY is equal to 6.8 kilonewtons. And By is equal to 3.2 kilonewtons. Okay, so let's first off, let's draw our axes for our shear and moment diagrams, right? Because we're going to want to create these shear and moment diagrams in a way that makes sense. So here are some graph axes. All right. Let me just extend this one out here. Oh, there it is. Oh, come on. There we go. A little more. Oh, come on. All right. Ah. Okay, there we go. Okay, great. All right. So we'll start out with A to C, right? So basically 0 to 2 meters. Okay. So we draw the free body diagram. What we're going to do is we're going to draw the free body diagram for just some random section through here. So let's say we're going to cut it there, right? That means we're going to be distance x traveling along the beam. We've got our AY. We've got our shear and our moment. Now, and then our 4 kilonewton per meter force. Okay, we have always said just draw the unknown force and assume it in some direction. And we've never really told you you need to do it to always assume that force X, B, or Y, or whatever is in this particular direction. For shear and moment diagrams, and this is really the only place in statics where we're going to do this, well, with the exception of friction that we'll talk about later, but for just general free body diagrams, shear and moment diagrams are the only place where we're going to tell you there is a sign convention. And that is, if you are traveling through the beam from left to right, you orient the shear downward and the moment in the positive direction on the cut face. If I was going from right to left, I'd do it the opposite direction. So if I was going from right to left, here's BY, right? And then maybe we've gone far enough to include that one. Here we're going to have the shear pointing up and the moment being negative. Okay, so again, keep in the sign convention is when going from left to right, like you read a sentence, the shear is pointing down and the moment is positive. When we were going from right to left, the shear is pointing up and the moment is negative. And the reason that we do this is so that when we draw our shear and moment diagrams, everybody sort of knows what positive and negative means. It will have an additional benefit of letting us do what I like to call shear pushing when we start drawing our shear and moment diagram. So again, V and M. Okay. All right, so first things, we've got a free body diagram here of some cut that we've made in the middle of region A to C. We can sum our forces in Y and figure out what our shear is. So we've got AY, right? And then the other thing is we have a portion of this 5 kilonewton per meter load. So we have minus 4 kilonewtons per meter, but the distance we don't know, so we'll just call it X, right? So we're some distance somewhere in the middle here. We're not the whole piece, just we're writing the free body diagram of us making some arbitrary cut X distance away from the left-hand side, right? So we've traveled X, we make this cut, and then we draw this, and we say the distance we've traveled is X. So again, right, we're making a function, basically, a y equals f of x going from A to C that tells us the moment. So AY minus this minus the distributed load minus the shear equals 0. And so that tells us V, the shear, is equal to 4 kilonewtons per meter times X. And then that is negative, right? Oh, well, actually, yeah, that's negative. And then plus AY. All right, so we can go over here and we can write, and I'm going to draw some green lines here to, maybe those are green, I don't know, I'm sort of colorblind. Some separation lines here, they're not, they're black. And to help us separate this shear and moment diagram out in these pieces. Okay, so at x equals 0, or the beginning of the beam, our shear is equal to AY. And so AY in this case, right, is 6.8. So we'll put a little dot here. We'll write 6.8. So there we go. And then this is a linear function, right? It's something times x plus AY. So this is the equation of a line. And so what happens is we just decrease linearly down to the value here at 2 meters. And when we calculate that value, we find that this is minus 1.2. All right, so that is the shape of the shear curve, or the shear value, in this beam going from 0 to 2 meters. So get rid of that. All right. Next, we'll do the moment. So again, right, so here we have some moments. I'm going to do it at the cut, right? So I'm going to do it about point X, which is this point right here. That gets rid of the shear, and then we only have these pieces here. So the first one, right, so we have AY is acting distance X from the cut, and that's creating a negative moment, so minus AY times X. And then we have this distributed load, and we have a section of the distributed load, right, 4 kilonewtons per meter. It has a reaction force that acts in the center of this cut section, so right here at x over 2 from the cut face. So that's a positive moment. So we have 4 kilonewtons per meter times x, right? That's the total force. Total force. And then we have to multiply it by the distance, x over 2. Okay, so there we go. AY times x, 4 kilonewtons per meter times x over 2 plus m equals 0. And then we can go ahead and solve for m. And what we find out, right, first off, we can see at x equals 0, our moment by definition has to be equal to 0. And then it basically is just negative all the way to the final value here, which turns out to be minus 5.6. All right, and it kind of doesn't matter, just sort of draw a curve. There's probably an inflection point in there somewhere, but we don't care. This is an art piece, right? So we're just saying straight line and then a curved line. This is quadratic. You can label that if you want. All right, so there we go. Now we're done. We finished from A to C. Now we need to go on to the next one, from C to D. All right. So draw a free body diagram. AY, shear, moment. Now, when we've basically gone through AC, the amount of this distributed load that we're going to be needing to take into account as we cut and make a cut is fixed, right? It doesn't change anymore since we're out here. So if we're standing out here, just standing on the beam and looking back that way, we see the whole load, right? We don't see part of it. If we were in here, looking back that way, we'd only see the part in front of us. So we'd only see, let's say, that much of the load, right? But since we're out here, we see all the load. So what that lets us do is, instead of having to write a function versus the distance for the load, we can see the whole load. And so we can just replace that with a single 8 kilonewton force acting in the middle. And this is true for all distributed loads. So 8 kilonewtons, 1 meter, right? And there we go. So now we can sum our forces in the y. So again, we have AY minus 8 kilonewtons minus V equals 0. And so that is convenient because that tells us that V is constant, right? There's no X, so V is constant, which should make some sense, right? There's no forces in this region to generate a change in shear. So this is 6.8, right? And 8 minus 8, and so that's 1.2. And so this is just a straight line, 1.2, or negative 1.2, the whole region from D to B. All right. We can sum our moments in the X at the cut again. So again, we're summing it right here. And so we'll start with we'll start with the moments. Positive minus AY. Again, we're distance X from the cut, or from this point right here. And then this 8 kilonewton, right, we're a distance, we want to know this distance, right? So if this total distance from here to here is equal to X, then our 8 kilonewtons, X minus 1 meter equals 0. All right, so notice we've gone from a quadratic equation for the last one to now a linear equation, and we'll talk about why that is in a bit. So when we have x equal 2 meters, we plug this in here and we find out we're 5.6, which is good because if we weren't, then we'd have a problem. And then when we plug in x equals 4 meters, when we're at this point, we end up with this basically have slightly increased to minus 3.2. All right. Fantastic. So now we finally do the last section. So again, here is the AY, X, V, M. We've got our 8 kilonewton force, our 2 kilonewton force now, and we can go ahead and start solving this. So some forces in the Y equals 0. So we have AY minus 8 kilonewtons minus 2 kilonewtons plus V, or rather minus V equals 0. And so when we plug that in, V jumps down immediately down here to minus 3.2 and then is continuous. And then summing forces at the cut, or rather summing moments at the cut. So again, we're summing the moments about this point X, right at the end of the cut face. We again have AY, well, let's see, okay, so 8 kilonewton X minus 1 meter plus 2 kilonewtons. And this is acting, right, this one acts 4 meters from the end. So that is X minus 4 meters. Then plus M, and then our AY is minus AY times X, all equals 0. When we do that, we plug in 4 meters and we get minus 3.2, and we plug in 5 meters, we get 0. Which is good. Okay, so that we'll talk about why that's good in a minute. All right, so what we're left with here is basically a graph that shows how the shear changes through the material, and then a graph showing how the moment changes as we travel along the beam. So again, these represent the continuous distribution of shear and moment throughout this beam, which is the goal. Now, some of you may be saying, hey, but when we make this cut, there's all these forces over here that we look like we're throwing away. What happened to those? And the answer is those are contained within the two reactions. Remember, you solve these two reactions globally, right? And you've got the entire, oh no. Oh, sorry, the entire thing. Sorry, I thought I wasn't recording for a second. So these two reactions right here are contained globally. You've got the whole thing. Whoa, they're covered. Everything is covered. So these forces AY and BY contain all the information about all the distributed loads, so you don't have to worry about it. They're contained already in the information of the system. And that's all there is to it. You look at every single time this changes load, you draw another free body diagram that represents some sort of intermediate position that you label as distance X, just like you would on a graph. And then whenever you hit the end of this, you draw a new one, and then there's a change and you draw another one. Another thing that you can look at is there's what I like to call shear pushing is occurring. So each one of these forces pushes this shear curve around proportional to the amount of force, right? So AY is a point load, so we go straight from 0 to 6.8, the value of AY. Then there's a distributed load which is pointing downward, so it pushes this curve down, 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 down until we get to minus 1.2. Then there's no forces here, so there's nothing to push it around. Then we hit minus 2 kilonewtons and it pushes it down to 3.2 kilonewtons, and then we run over and we hit BY, which is minus 3.2 K, and we go back to 0. So again, having the sign convention such as it is right here allows you to basically just read off the shear diagram from the force of the free body diagram. So if you screw up your free body diagram, you're going to screw up your shear diagram, and you won't be able to do it. You can also notice too that this curve here is quadratic, this is linear, and this is constant. Somebody, if you're thinking a little bit ahead, or you're really observant, you'll notice the derivative of a squared is a linear line, right? So the derivative of a quadratic is a linear, and the derivative of a linear is a constant. So there is some sort of derivative integral relationship here between moment and shear and load, which we will talk about on the next one.